Hey guys, so in this video I'm going to talk about equations of fluid dynamics. Um, the reason why we need to cover this is because, well, we're talking about aerodynamics and air is in fact a fluid. So equations of fluid dynamics will let us know how an air goes around a certain object and also how the motion of air can be used, by tracking the motion of air can be used to determine lift, thrust, and drag. Those are the case basically four forces of flight, right? So I put a picture here from Srinivasa Ramanujan. An equation means nothing to me unless it expresses a thought of God. So I'm not sure how many of you really understand the equations of fluid dynamics, but the reason why we need to talk about this is because as an aerodynamicist, you need to have an intuitive idea of what these equations represent, right? I mean, you don't have to go as philosophical as Ramanujan here, but at least the goal here is for you to not be afraid of the equations of fluid dynamics. It's not all, well, yes, it's a mathematical equation, but it means something real, something very real in physical space. Okay, so that's what we're going to uncover in this video, right? So let me move on to the slide again. The first video I'll be talking about using conservation of mass and momentum and applying it to thrust. In the second video, I'm going to talk about lift. And the third video, where you're going to use the conservations of mass and momentum to derive an expression and also calculate the drag or drag coefficient for an experimental data, right? And in the fourth video, I'll be talking about the energy equation. Um, so energy equation is we need to, well, you guys need to know what's the purpose of energy equation and how it ties in with equations of mass and momentum. For most incompressible flows, you can get away by not considering energy equation, but as you push the Mach number higher and higher, energy equations become exceedingly irrelevant, exceedingly relevant. So we will talk about in the last video, we'll talk about why we need to consider the energy equation in when talking about fluid flows at high speeds. All right, so what are we hoping to achieve? Well, first things first is you need to be able to explain equations of fluid motion from a physical perspective. By the time you graduate from this class, I want you guys to be able to explain and even write the equations of fluid dynamics in your sleep. And also using equation of fluid dynamics to derive expressions for lift, drag, and thrust, and also to calculate lift and drag using equation of fluid motion from experimental data, um, and also identify the equipment necessary and also the value to determine aerodynamic forces using equation of fluid dynamics instead of force transducers. So even though we can use force transducers to get lift and drag values, these sensors can range all the way from few $100s to several $1 million. So depending on what it is that's exactly that you need, you can either choose to go with the force sensor, or if you don't have the money or the means, you can always rely on the equations of fluid dynamics to get an accurate estimate of lift and drag and even thrust. Okay, that's the whole point of doing this. So, well, as you know, there are four forces of flight, right? Here's a cartoon which explains everything, the four forces in a way that is humorous. So, right, you got money, dreams, FAA, and reality. But in more, on a more serious note, you got this weight, you got lift, you got thrust, and then, well, you got drag, which, of course, an FAA has a lot of rules, which is why, you can think FAA has a drag component. Right. So, but again, these three forces can be derived from equations of fluid motion. And of course, you got the weight, but weight is kind of pretty much there for any material, right? Right. Let's start with thrust. Okay. Now consider this portion right here is the fuselage, and then you have the engine mounted to the wing or the fuselage. Um, and consider you have the air entering the engine with these properties rho1, v1, and p1. And in fact, you can add, you can assume that the area in the front is a1, and the air is exiting the engine at a different flow properties, right? Then rho2, v2, a2, and p2. And for now, let's imagine this engine is a black box and we'll just draw a control volume around it, right? Now, for the conservation of mass, I actually, put this equation right here. Um, I don't, uh, before you guys move on, I'd like for you guys to pause and just look at this equation and think about what it is that you get out of it, right? What it is that you see here, right? You got this first term is dt by dt d by dt of integral rho dot dv, right? You can see that the first term, if you actually look at the units, you get 1 over s and then kilogram per meter cube, which is density, and then you get the volume, which is meter cube. When you work out the units, it just comes out to kilogram per second. So all the first term is doing is in this control volume, right? In this control volume right here, all we are doing is tracking how the mass is changing as a function of time, right? So that means, for example, if you have a variation in mass as a function of time, then you know that either the mass is accumulating or it's getting removed from the control volume, right? So that's right. But at the same time, we kind of know that mass cannot increase automatically, right? Or even mass cannot decrease automatically because mass cannot be created or destroyed. So in the event that mass is increasing, that means there has to be some other element accounting for that increase, right? And that's where the second term comes in, which actually talks about mass entering and leaving the system, especially this control volume. So if you look at this, the units of this term, you get kilogram per meter cube, you get meters per second, and then meter square, which is basically, again, turns out to kilogram per second, right? So that means all we are trying to see here is that we are trying to estimate what is the velocity or what's the mass coming into the control volume and what's the mass going out of the control volume. What this all says is that, okay, the first term represents the accumulation of mass and the second term represents the mass flux. Okay, so what this says that if there is an accumulation of mass, then there has to be a mass flux component, which means that the amount of mass entering should not be, at least the mass flow rate entering will not be the same mass flow rate exiting unless, your d by dt term is zero. Okay, if this is non-zero, then you will either have mass accumulation or mass removal, right? So that's pretty much what this equation says. I hope hopefully you kind of get an idea of what these two terms in the conservation of mass equation represents. Okay, so now let's apply this conservation of mass to this control volume. Let's assume steady flow. So let's just assume this term goes to zero, right? There's no change in mass as a function of time. So looking at just a constant mass, right? And now all we have to worry about is the second term is rho v dot ds. Now, assuming that the area here doesn't change, right? Just assume that area as A1 and then here the area as A2. So that becomes a constant, so you could take it out of the integral. Or if you integrate, you will just get A1 and A2, right? So when you apply this to control volume here on one side and then the inlet and the outlet, right? So you have minus rho A1 V1 and plus rho A2 V2. Now you may think, okay, why is there a sign variance in these two terms, right? Remember that in the previous case, you have V dot ds, right? So this ds, the unit vector of this will have a directionality associated with that. So if you look at the unit vector in this A1, it's pointing to the left. If you look at the vector, the unit vector on this area is pointing towards the right. So of course, there are different different directions. We got to account for that, right? So that's why anything pointing to the left, we just note it by minus. So that's why you got the minus here. So rho 1 A1 V1 plus rho 2 A2 V2 because the ds is constant. Okay. Now, if you assume that well, if you assume the density is constant, then you can cancel out these densities and it will be rho 1, A1 V1 equals A2 V2. But for right now, let's just keep the density terms in there, right? Just know the conservation of mass, it represents how area and velocity is changing with one another, right? So that's pretty much what it is. Right. Now let's move on to conservation of momentum. So I'm going to put this equation right here. So for now, let's just look at the left-hand term. Now, I want you guys to pause here. Pause, go back a few minutes and look at the conservation of mass equation. Okay, look at the conservation of mass equation and scroll back here and then look at the conservation of momentum. Do you see any similarities, right? So let's recall. In conservation of mass, we had the exact same terms, but in the first term there was no velocity here, right? And this term is exactly the same term you have in conservation of mass, right? But it gets velocity multiplied by it. Now, think about this. Momentum is nothing but mass times velocity, right? So that means instead of tracking how mass changes inside the control volume, this first term, it kind of accounts for changes in the momentum inside the control volume. Again, there's dot dv because we have to account for the way or the direction in which velocity approaches this change in volume, right? So density times velocity, you get the momentum, right? You're tracking momentum as a function of time inside the control volume. That's the first term, right? The second term is basically, this is kilogram per second, right? This is the mass entering and leaving the system. All you had to do is multiply with velocity, then you will get momentum, right? Now, the second term accounts for change in momentum, accounts for momentum coming in and momentum going out, okay? If there's any changes in the momentum coming in and momentum going out, there will always be forces associated with that. And that comes from Newton's second law. Conservation of momentum is actually from Newton's second law, right? F equals ma. It's pretty much what this is. Okay. Now, thinking about all the different forces that can affect the motion of a fluid, you got the pressure, friction, and body, right? Now, let's just assume for now there's no friction and there's no body force. Now let's just consider the pressure alone, and we can represent this pressure force as pressure P times dot ds. Again, pressure times area gives you force, right? Again, there's a negative sign. Every time you deal with pressures in any equations, there's always a negative sign associated with that. The reason is because the pressure will always act inward. Okay, that's the only reason why you have pressures acting. Anytime you deal with pressure, you always have this negative sign in the front. Okay. Now, well, hopefully you guys understood this equation. Again, just an extension of conservation of mass. Apply this conservation of momentum to this control volume, right? Let's assume again steady flow. So just get rid of the first term and then look at the second term. And when you apply this, it's the same in a rho A1 V1. Again, there is a negative sign here because of this change, the ds unit vector, right? So except, when we compare to conservation of mass, we just got these rho 1 A1 V1, but guess what? Conservation of momentum, we got this extra V term that accounts for how mass is, what's the velocity that the moving mass has. So that means, the velocity coming in gets multiplied with V1, velocity going out gets multiplied with V2, right? So you got V1 square, rho A2, V2 square. Again, same here, same. So P is the pressure acting on P, one side, so inlet, this is the pressure acting on the outlet, right? So the ds on the inlet is negative, so negative and negative becomes positive, and then the negative stays for the rest here, right? So P1A1 minus P2A2. But notice that I also added a reaction force right here. The reason why we have to account for the reaction force is because the engine is actually adding work into the flow, into the control volume, right? Or into the air, right? So that means, according to Newton's third law, the air in turn exerts equal and opposite force to the engine, which is what we call thrust, right? So that's why equal and opposite, that's why you get minus T. Sorry, just do that. Yeah. So Rx equals minus T, so minus and minus becomes positive, so you'll actually get plus, right? Now, in this step, what I did here is took the conservation and took the mass flow rate as common. Rho A1 V1 is mass flow rate m dot. And if I take that as a common term, we know that rho 1 A1 V1 equals rho 2 A2 V2. So that means I can substitute this as rho 1 A1 V1 times V2, and I can back out, I can, take out V, what will remain is basically V2 minus V1 in this parenthesis, right? The rest all here is the same. Now, rearranging this equation for thrust, this is pretty much what we got, right? Thrust equals mass flow rate times velocity 2 minus velocity 1 minus P1A1 minus P2A2, okay? Now, let's look at the context of actual engine, right? So this is the equation that we actually just derived. Thrust equals mass flow rate exit in times velocity exiting the engine minus velocity coming into the engine minus P inlet times A inlet minus P exit times A exit, right? But we can actually write, we can combine the exit, area exit, and pressures in this way. Again, there's a reason, okay? Now, P inlet, if you guys think about what P inlet actually is, P inlet is nothing but the ambient pressure, right? That's the pressure at which the velocity is actually coming into the engine, right? Now, if you want to look at the performance of the nozzle and the engine, what's really affecting the force is how, or the balance between the ambient pressure, which is basically P inlet, and the exit pressure, and how these two pressures acting on an exit area of the engine. Okay, that's why you can represent the same thing, but in terms of just the exit area alone. Okay, because ultimately what really matters is that what is the variation, what's the force that is exerted due to the changes in the exit pressure and the ambient pressure. Okay, now let's just look at this term alone, so that you may get a better idea. Now watch this video. I'm gonna play this video right here. So, oop, sorry, oop, hold on. I want my uh, right. Here's an Apollo 11 launch, and look, just keep an eye on the exhaust. Look what's actually happening to the exhaust. Okay, now it's the rocket is at about 15 kilometers and climbing. Just watch the plume. Look, look what's happening, right? So as the rocket climbs up the altitude, the the plume that's coming out of the engine actually increases in its area, right? Now, think about this. What do you think that's going to do to the forces or the thrust experienced by the rocket, right? So this, this phenomenon actually has to do, it can be represented by this equation right here, okay? Let's think about this a little bit more. The ambient pressure is about 100 and what 101 kilopascal, or it's about 14 psi, right? And any velocity that is exiting the engine will have a really high speed. So that means your static pressure will be very low when compared to the inlet pressure. Okay, so that means at lower altitudes, your exit pressure will always be less than the inlet pressure. So that means this term will always be negative. Okay, and the problem is that this second term is actually, reducing the overall thrust that the engine produces. Because look at that, T equals this term minus this term. So if this term is higher, right, that means you're getting less thrust. Okay. Now you can see the same phenomena in this here, right here, right? So if your atmospheric ambient pressure is greater than the exit pressure, you will actually see what is called shock diamonds. So you'll see here, so these are all shock diamonds. It's coming out of the SR-71, you got the rocket, you got the F-15, and you even have the space shuttle, right? You got the shock diamonds. But as the rocket climbs up the altitude, as you can see, as you saw in this video, your let me go. Your ambient pressure goes down a lot, right? At some point, your exit pressure will be equal to the ambient pressure. And guess what? That's actually the design, condition for a nozzle, right? Especially for this SSMEs. When well, if you take compressible flow with me, one of the things that we will do is optimizing the spatial main engines, and you will soon find that using simple analysis, the altitude at which the rocket engine the SSMEs operate efficiently is about 12 kilometers, because that's where the ambient pressure actually matches the exit pressure. And when that happens, there will be no shock diamonds, there will be no expansion waves. Like the flow will be completely isentropic. So right, that's when exit pressure goes goes more or increases more than the ambient pressure, you can see that it actually contributes to thrust. But you will have losses in terms of nozzle efficiency because you have expanding air. Okay. Now let's look at the first term. We talked about these nozzles. So uh, yeah, I'm going to skip that. So we'll talk about the nozzles. Let's look at the first term, right? The way to increase thrust is either by increasing the exit pressure, or you can decrease the inlet pressure, right? Or inlet. Or the way to increase the thrust is by increasing exit velocity or reducing the inlet velocity, because this term is actually reducing it, right? Now you may think that, hey, I'm just going to push the air as fast as I can using my engine. But guess what? When you push this air fast, right? Say you're pushing the air at supersonic speeds, and the airplane is going supersonic. But the problem is the velocity entering the engine is also supersonic, right? So if the momentum coming in matches the momentum going out, your thrust will be zero. Okay, so it's not just the Newton's third law which is contributing to thrust. Okay, in jet engines, the major thrust, is it comes from Newton's second law, right? That means it matters how much change in momentum that the engine has to make between the air coming in and air coming out. If the momentum difference is not great, then you won't be producing any thrust. Okay, so now how do you account for that? So when airplanes go supersonic, the airplanes have different types of inlets: 1D, 2D, and 3D. In all of this, we'll talk about in compressible flow. But what the job of these inlets is basically take a supersonic air, reduce the momentum, right, and then so that the engine right here will increase its momentum and then push the air more, right? So that there will be a change in momentum coming into the engine and then going out, which produces net thrust. Okay. So here are some examples. It's an F-16 with an 1D inlet. You have the F-15 with a 2D inlet, and an SR-71 and has a 3D inlet. Basically, the job of the inlet is to reduce, the inlet air coming in. So I just want you guys to kind of have a sense of how just simple conservation of momentum equation can give such a beautiful expression for thrust that it can be used to design an actual engine. Okay, that's the beauty of these equations. So in the next video, I'm going to talk about lift. All right, I'll see you guys in the next video.